Dr.
Uh, Hello, everyone. We'd like to starting this webinar and in collaboration with the IEEE West Saudi Arabia section. This will be Connecting Experts series for November, Transformer, Differential Protection Theory and Testing with Engineer Ahmed. The moderator will be Engineer Ibrahim Al-Mohseni. So the floor is yours, Engineer Ibrahim.
Thank you, Doctor. Welcome everyone. Thank you for joining us for today's webinar as a part in IEEE Connecting Expert program. I'm Ibrahim Al-Mohseni, an industrial relations coordinator in IEEE Western Saudi Arabia. I will be the moderator of today webinar. Today we are presenting an important topic in power system. Exactly in power transformer protection as a topic, transformer differential protection theory and testing. Now we will turn the time over to Engineer Ahmed. Our presenter today is Engineer Ahmed Abdul Wahab, expert in Omicron Electronics Middle East. He has 15 years experience in protection and testing field. Engineer Ahmed, the floor is yours now. You welcome and you can start.
Thanks, Engineer Ibrahim. Thanks, Dr. Ali. I would like to take this opportunity to thank the IEEE members and the IEEE Quit Student Chapter for this golden opportunity for me to meet all of you. Just for the time's sake, I would like to share my screen and I hope you can see it at the moment. And just a minute. So you can see it right now.
Yes, Engineer.
Thanks. Just a minute, I need to swap. Yeah. So I would like to thank again all attendees and Dr. Ali and Engineer Ibrahim for this opportunity to meet all of you. My name is Ahmed Abdul Wahab. I'm working as application and sales engineer with Omicron Middle East and Africa. My main responsibility is the GCC country, especially Saudi Arabia. And today we are gonna talk about transformer differential protection, the 87. My short biography, I'm graduated from Ain Shams University, 2006, electrical and power machines. I have a diploma in the field of system studies, transient simulation with ETAP. And I have experience of 15 years in the testing and commissioning field, especially in GCC country. Joined the Arabian PIMCO as a commissioning engineer in Saudi Arabia, then joined Siemens Saudi Arabia till 2017. And currently I'm sales and application engineer in Omicron Middle East since January 2018, providing technical support, on-site training, customized training, and protection testing templates for high voltage and extra high voltage transmission systems and distribution network. My contact details, you are most welcome to communicate with me at any time. Feel free to text me on WhatsApp. I just put my mobile number here and I put my email, as well as I put the QR code for my LinkedIn profile. I would appreciate to communicate with me anytime for any technical inquiries. So now let us talk about the transformer, the basic physics, which we are really interested. We know that the transformer consists of a windings, consists of a tank, oil immersed, and bushing, but this is not our main topic. Our main topic is the equivalent circuit of the electromagnetic circuit and the equivalent circuit, the electrical one. The equivalent electromagnetic circuit, it's very, very easy for us that we have high voltage side and we have a low voltage side if it is a step down transformer, or we have a low voltage side and high voltage side if I have a step up transformer. When I apply a voltage U1 on the winding, the high voltage side, current will flow. This current using Farad law, sorry, that it will a current will flow and it will induce a flux. This flux need a media to move in it because it can't go in the air, as it will be stray here on the other side, but it need a magnetic flux or a metal. So we have the magnetic flux or the iron core of the transformer. The magnetic flux will travel through it and it will cut the winding of the low voltage side or the other side. Flux with the winding, it will generate and induce EMF. And this EMF, we have a load here, so it will flow a current, I2, and this current with the impedance of the load, this will be like a developed voltage on the low voltage side. So we have a U2 here. So it's very simple physics. I have applied voltage, current will flow, current will induce a flux, flux will travel in the iron core or the magnetic field, and the magnetic field will intersect with the winding of the low voltage side. This current will flow with the I2. I2 will flow in a load, and this load will develop a voltage. So we have here U2. The flux is divided into three parts. The first part is the main flux, which is phi, which is responsible to induce the EMF in the low voltage side. But there is a phi, which we call it phi sigma 1, and phi sigma 2, which we can consider it as a losses. So as we know, in every system we have a losses. So the losses in the magnetic field here, we have phi sigma 1 and phi sigma 2. This is, we call it the equivalent electromagnetic circuit. Since we are not talking about the magnetic field, we are talking about the electrical field. So we need to simulate the transformer from the impedance perspective or resistance and reactance perspective. So I have a winding here. This winding has a resistance and reactance. So I have here the R1 and the reactance, which simulate the losses in the field. So it will give me X sigma 1, which is the reactance. And the iron core, I can represent it in the XM, which we can call it the magnetic or the magnetization core with a value XM. And the low voltage side or the other side, I have also a reactance, which can simulated by X sigma 2, and the resistance of the load, which we can call it as R2. Sorry, the resistance of the winding, which we can call it R2. Very simplified circuit. Yes, we ignore here the RC, which we call it the core resistance, because we can consider it with very high value, and we can consider it as an open circuit. So the U1, the applied voltage on the high voltage side, it will face the R1, the resistance, and X sigma, and you can see here, it's written directly as R1 and X sigma 1. But on the other side, you will see here U-2 and R-2, X-2 sigma 2, and I-2. What is the dash? Dash, because we need to refer the impedance and the reactance and the voltage and the current from the low voltage side or from the other side to one side, because I can't gather both of them in a one electrical system with the two different bases, because here the base is U1, for example, and the base here is U2. So I need to refer from this side to the other side. And the magnetic core, I have here the magnetization current, which you can call it IM, flowing in the reactance XM. IM is a magnetization current, and it is very, very important. We will see later how this magnetization current will affect on the transformer performance. This is a simplified electrical system and electric equivalent circuit, and simplified as well equivalent electromagnetic circuit. The 8070 function, very, very important, very, very simple, but it needs some awareness about it. Based on the current comparison, because we study all of us the Kirchhoff current law, KCL, which said that the summation of all currents in and out of any electrical node should be equal to 0 in case of a stable condition or in case of healthy operation. Or in other words, we can say that all current in should equal all current out, taking into consideration the vectorial direction. What does it mean, the vectorial direction? It means that I need to assume a reference direction which going inside the node, which can say positive, and the current leaving this node should be negative. Hence, I can submit all current, and at the end, if my system is stable or healthy, the summation of all current equal 0. Very simple vectorial representation, that one absolute will be equal 1 with angle 0, and negative 1 will be 1 with angle 180. Here we have also in a vectorial summation or a vectorial direction. When comparing all current, we will use the fact that the protected object, the summation of all current should equal to 0, which we can say this is normal operation, current in, current out. This is from the Kirchhoff current law. And let us look at our system. If I have the protected object here and I have a fault in the protected object, you can see that all current, as all of us know, the current will flow in the direction of the fault. So I have here a short circuit. Current will go to the fault point from this side, from the right side, and the current will flow from the other side to the fault. So I have here both currents flow in the same direction. All of them are in. So this will be positive, the other side will be positive. If I use the very basic definition of the differential current, which is, it is the summation, it is the absolute value of the vectorial sum of all currents in and out. So I have a diff in a stable condition that I have I1 equal to I2, and we will ignore the losses in our system. So I diff in case of normal load or external fault, I will equal I plus in bracket minus I. So in overall, it will be equal to 0 in a stable condition. Let us say in case if I have faulty condition, what will happen? I have I short circuit 1 flow inside the protected object, and I have I short circuit 2 is flowing also inside the protected object. So this will be positive, this will be positive, and we don't know the contribution from this side and the contribution of this side because it depends if I have a load here or I have only in feed. So we will make it in general that the short circuit case, the I differential will equal to I short circuit 1 plus I short circuit 2, which can give me a significant value. In ideal case, I short circuit 1 will equal to I short circuit 2, and we will give them a general name I short circuit. So the differential current will be 2 I short circuit. The differentiation between the two currents, the current in and the current out, is a clear indication there is an internal fault. Let us assume I don't have I short circuit 2 because I don't have anything here on the right side. So I have I short circuit in, but it doesn't go out. Who will tell me that this current in or out? The CT. So the definition of the protected zone is the CT. So the area between the two CTs, I can call it the protected zone. If a current bus is like a monitor or a guard, if the current bus on the CT T1, but it doesn't reach to a CT T2, it means there is an internal fault. Here, the definition or the differentiation. So the element, the protected element will differentiate between the current signal will come from CT T1 with the current signal come from T2. If both of them not equal to each other, so it means I have a fault, internal fault. If both of them are equal, so it means that either I have an external fault behind this TT or I have a normal operation. This is the main idea about the 87T protection. Transformer differential should give me very, very selective protection and should work in this case to detect all ground faults and multiple short circuit in case of transformer, generator, reactor, short lines, as well as motors. But with every protected object, I need to understand the physics, the phenomena which will happen with this protected object. For transformer, I have so many parameters will affect the differential protection. I need to put it into my consideration when I am setting this relay, when I am testing this protection. With the reactors, I have another phenomena, like in the reactor, I don't have a low voltage side or I don't have side 2 because it's just a coil connected to the ground to give a neutral point to the line. Short lines, there is no vector group, there is no vector group, there is no phase rotation, there is no change in the current value due to the turn ratio of the transformer. Motor and generation, there is nothing to change. The current in equal to the current out from the neutral side and from the line. The transformer differential can work in a block condition. That's why I need to say it's selective and also secure, because in the power plant, I have the generator very close to the transformer, the GSU, or we can say grid step up transformer. So if I combine both of them, generators and the transformer, I can say this is a block or this is a unit. So I need a differential protection to work to cover all this block. So I call it block function. Stable against heavy external fault, because usually in the power system, I should have external fault, internal fault. And as we said, based on the physics, that the protected zone here in this slide is the definition, is a defined area between the CT1 and CT2, or a T1 and T2. So if I have external fault here outside, I can draw it with a pen. Just a minute here. If I have a fault here, so this say it is outside my protected zone and my system should be stable. So the differential protection should be stable against the external fault. And all other phenomena might appear during the external fault, because I can have external fault very close to the CT, and the CT might be saturated. And in case of the CT saturation, which you will hear it frequently when you are dealing with the differential protection, if the CT saturated, that might happen that the current signal come from the CT, which is saturated, not equal to the current comes from the CT, which is not saturated, and this can lead to a misoperation of the differential protection. We have a way to overcome this. Yes, we have. We will talk about it in the operating characteristic in the differential protection. So this is which we can say this condition, or this is phenomena, or what you can call it. We can call it security, that our protection system is very secured against the external fault or against the normal operation heavy load. And the second thing, or the second main characteristic of the protection system, it should be selective. What does it mean selective? It should trip on the case of internal fault. So this is here. I should have also my protection system is very selective. So the main requirement of any protection system, it should be selective, trip on internal faults, and secured, doesn't trip in case of the external fault, and stable against transient condition like inrush and overexcitation. This is the main characteristic, or the overview of what the differential protection should do to say that I have a good protection, a good differential protection. Now, let us see what are the challenges in the differential protection system in case of a transformer, and we will see how we will overcome it. This is a very old differential protection scheme. I worked in it in Saudi Arabia in the year of 2008. Transformer, high voltage side, 132/33 kV. I have a high voltage side, which is star, and you can see it is a star transformer grounded. And the other side is a delta, which is a low voltage side. What should I do? To compare between two values, I should have reference. I can't compare 1,000 with 1 million, because I don't understand to whom which I'm comparing. Because if I say 1,000 relative to 1 million, it's a great difference. But if I say 1,000 compared to 1, so 1,000 is a great value, 1 million also the great value. So I should have a reference. So the reference in the electrical system or in the transformer, you should define it before the numerical relays, or in a static relay, or we can call it the high impedance relay. This is a high impedance differential protection. We are doing everything. We are doing every mathematical calculation outside the relay. And finally, we are giving to the relay current, which is ready for comparison. So what I'm doing is I have a current here, high voltage side. First of all, we calculate the full load current. Then the full load current, I need to decide or make CT dimensioning how much the current the CT ratio I need to have a significant full load current. So we need to decide 200/1. And I need to put in consideration as well the directionality. Where is B2 and B1? And all of us know the importance of directionality in case of differential protection, because we said differential protection depends on the directionality. The current in will be positive and the current out will be negative. So if I compare, or if I use a wrong directionality terminology, so it means at the end, I will see the current swapped in a wrong direction, and it might operate in case of external fault and doesn't operate in case of internal fault. So I need to define that, where is the P1 and P2. And from this, or from the CT itself, I can say that we have two types of the directionality or the polarity. The correct word is the polarity. The polarity of the CT, that in case if I have in the first sinusoidal, the current is positive sinusoidal wave, and the first half cycle, and in the second half cycle is negative. So if the current is flowing from P1 to P2, so the secondary current will be in the opposite with a 180 degree. So it means the current is flowing from P1 to P2, the other side will be from S2 to S1. This is to simplify the calculation. Then I need to calculate the resistance. I need to calculate the high impedance resistance to limit the voltage or to generate a voltage which the bias differential protection needed. What else I need? I need to do something which is, call it adaptation. Adaptation of the current in from the CT, because I have two different values. I have U1 and U2. I have I1 and I have I2. The high voltage side, the low voltage side, the high voltage current and the low voltage current. And both of them not equal in magnitude, and both of them, they have a different angle. Because of what? Because of the vector group. So if I have a transformer of vector group 1, so let us say that I have phase shift between the two sides, side 1 and side 2, by angle of 30. The current on the other side lags the current on the high voltage side and the low voltage side by angle of 30, so it will be minus 30. If I give the differential relay two different current with a different magnitude, with a different angle, at the end, the differential relay will detect a current and it will give you trip in case of the system is stable. So what should I do? I should do all of this calculation from both sides to give at the end the current adapted to each other and ready for comparison. This is what we call it bias differential scheme in case of a high impedance or static differential protection. If you need more details, I will give you a reference that we call it line differential or numerical differential protection for Dr. Gerhard Ziegler. I will share the reference with Dr. Ali and Engineer Ibrahim to share it with all attendees. You will see more details about this type of protection, how we can do the calculation. Now, nowadays, I don't need to do any kind of a calculation. I need just to have a protection relay, which we can say it here, the comparison of delta I, this is our numerical relay, and everything will be done inside the protection relay. I don't need any CTs. I don't need any polarizing calculation. I don't need to have a resistance. I don't need to find the interposing CT. I just need to define the transformer itself to the relay, the vector group, define the polarity directional, the polarity of the CT, and at the end, the relay itself will calculate. This is, we can say it, the numerical differential protection. So the item correction before comparison need to be done not by the way that a resistor and CTs, but the way of numerical. So let us say, what are the correction I need to define or I need to do before comparing? The first one, normalization. This is the first and the most important adaptation I need to do. Why? Because I have a transformer here with a number of turns or a number of windings W1, and I have a number of winding W2. I need to bring both sides to one base value. And here you can understand the importance of the per unit system. So I need to bring the high voltage side and the low voltage side to a per unit, to the same base value. So I need to think what is the most important and the most valuable parameter in the transformer, which is fixed between the high voltage side and low voltage side. The power, the apparent power, S. The apparent power for high voltage side is equal to the low voltage side because it is the same equation. S equal to square root of 3 multiplied by I multiplied by V line to line. So regardless the value of the voltage, regardless the value of the current based on the Turner's ratio, at the end, the value is megavolt ampere or kilovolt ampere is same. So I need to bring all of them to the same apparent power, which is the reference value. So I need to make it normalization. So I need to normalize the current secondary and the current secondary, but here in GA capital, which is the primary side, and GA secondary, this is from the low voltage side. So I need to normalize. Then I need to do something important. What is it? The I0 sequence elimination. What are the I0 sequence elimination? This is a challenge, can happen in the case if I have a transformer, star winding, and the star is grounded. What will happen? Let us see here. I have this star side, and I have a fault here external in this side. So I need the current need a closed path to flow or a closed loop. So what will be the directional if I have a fault here? The current will flow in the phase, then it will go to the ground, and from the ground to the other side. But the fault is already outside the protected zone. So what should happen? I should not trip. The relay shouldn't trip. If I didn't put this kind of a comparison or this kind of a correction into my consideration, the differential protection will trip in case of a single phase protection, single phase fault with external fault, because the actual differential current will be divided by square root of 3. So if I compare the current from the side, from the secondary side with the current from the primary side, I will see a difference of 2 over square root of 3. This is significant enough to make the relay trip. So I need to tell my relay that do correction of the I0 sequence elimination. This kind of correction happen only in case if I have a star grounded transformer. But in case if I have a delta, it's useless. I will not do it, because if I have a single phase fault, which is very, very rare to happen in a delta side, the current, the zero sequence current will be trapped inside the delta winding and it will not flow outside. So I don't care about the current will go to the CT. This is happen, but since it is, I'm standardizing the process now for the correction, I need to put I0 sequence elimination for delta, I0 sequence elimination for star. But in case the side is a delta, I need to override this and I will cancel it, but I will perform for the other side. Then the vector group compensation or the vector group adaptation. You will see here, the vector group adaptation happen only in the delta side. It doesn't happen in the star side. And here, I need to go back to the same point. I need a reference. So usually 99.9% of the protection relay need a reference, which is the star side. So I will say that the star side is my reference winding, and I need to bring the delta current, the delta side, then I will rotate it back to the star side to avoid the phase rotation or the angle happen due to the vector group. We have a great table of the vector group effect that in case if I have 1, 2, 3, 4, that the current will be lagged by angle 1 multiplied by 30, 2 multiplied by 30, 3 multiplied by 30. So the vector group adaptation will happen only on the delta side. Afterward, the current will be ready for the comparison. But I did here this kind of adaptation based on the steady state characteristic. But there is a lot of errors will happen during the normal operation of the transformer. I need to take care about it to avoid that the system will trip or the transformer will trip in case of the normal operation. So what should I do? I should put in my consideration during the calculation of the relay settings. So what will happen? We define 2 elements, because the first element I defined is the I differential with the differential current with the output between the 2 comparisons from the high side and from the low side. So that will calculate here the differential current of IA double asterisk with the I capital A asterisk. This is the two currents which are ready for comparison. From these two currents, I will calculate the differential current for phase A. And in the same IB double dash and IB capital dash or asterisk, I will calculate the differential current of the phase B. But let us say something. I'm pretty sure that the CT ratio here is not typical to the CT ratio here, or the accuracy of this CT is not typical the accuracy of this CT. Second thing, the resistance here in this not equal to the resistance in this loop or this bus. So many parameters. So what I need to do is I need to define a minimum operating or a minimum differential current to avoid the operation of my protection relay in case of a stable condition. I should reach to this value to think that, okay, it might be a fault due to this differential current, but it's not sure. I'm not sure. So I defined the minimum operating differential current, but this is not enough because there is a phenomenon might happen more than the CT ratio. Maybe happen that due to the CT saturation, maybe happen due to the magnetization of the current, which we'll talk about it later. So I need to define a parameter, try to stop the relay from the operation, like you are pushing the door to open, but someone is behind, block the door. You are trying to push to open the door to trip. This current, we call it the restraint current or the bias current. So many terminology for the same parameter. So we define the bias current, and you need to go back to your relay to understand exactly how the bias current will be calculated. Because from Siemens relay, it's different from ABB relay, it's different from Schneider, it's different from Schweitzer. Every manufacturer has its own bias differential equation, but all of them, they have the same differential equation, depends on Kirchhoff current law. After that, I need to draw characteristic between the differential current and the restraint current. As you can see here, I draw a relationship between the I differential, which is equal to the absolute value, as we said, I primary minus I secondary, or you can say plus, as you wish. But when you say plus, you need to have this negative. So in general, it will be IP minus I secondary. And I bias, this is the very basic formula, equal to the I bias absolute value plus I secondary in absolute value. And I plot both of them against each other to have a characteristic. We call it differential operating characteristic. And this differential operating characteristic, you should put in your consideration, it's a scalar characteristic. It's not a vectorial characteristic. The vectorial happen here under this calculation of I bias, of I differential and I bias. So it is a scalar relationship between two component or two parameter, which is the differential current and the bias current. And as we said, you need to go back to the relay manufacturer or the relay manual to get the equation of the I bias. From what this characteristic consists of? It consists of ID greater, which we said this is the minimum operating current, which we define it to avoid the main error of the CT ratio. And I have ID greater, we call it the unrestrained differential current. What does it mean, the word unrestrained? We will understand it right now. And the area between ID greater and ID greater, I have a characteristic, slope equal 0, or we can say, call it the flat region, slope equal number 1, slope equal number 2. So you can see it's a line, it's a segment. So it has two slopes, slope S1 and slope S2. And we define the area under this slope 1, slope 2 as a blocking area. And we define the area above slope 1, slope 2 as a trip area. The value of S1 and S2 depends on your system calculation, because You need to go back to your nameplate of your transformer, understand the magnetization current, because the magnetizing current, if you understand or remember from the equivalent electrical circuit, it's a current in passing through the iron core, but it's not leaving. So it is a normal differential current. You should put it in your calculation. So the magnetization current, which is IM, flowing in the XM. So this is a normal error. The second one, tab changer and leakage. If we remember from the electromagnetic circuit, I have phi, and I have phi sigma, and I have phi sigma 2. Phi sigma 1, phi sigma 2, this is a stray or a losses. I need to put it also in my calculation when I am setting up the calculation of the relay, because the other side, the high voltage side, will see phi equal phi, the main phi plus phi sigma 1, but the other side will see phi and phi sigma 2. Both of phi sigma 1 to phi sigma 2 is different. And also the tab changer. In many cases, in a big grid like Saudi Arabia SEC, during the summer especially, they need to regulate the voltage of the network to maintain the voltage in your socket around 220 volt. So they need to sometimes to increase the voltage at the substation or decrease it to avoid over voltage and under voltage. This has happened with something we call it tab changer. We have two types of the tab changer. We have off-load tab changer and we have on-load tab changer, OLTC. OLTC is most common because the offload, I need to switch off the transformer, change the tab, then switch on. This is interruption in the power system. But in the on-load tab changer, I can regulate the voltage while the transformer is running. This kind of on-off, increasing the tabs, reducing the tab, can generate a circulating current in one side, but the other side didn't detect. This is also a kind of a differential current. I need to think about it. The second and the most important one, or the most important error, is a saturation. Because we said that maybe I have a fault very close to a one CT, and this CT will be saturated, and the other CT on the high voltage side is not saturated because there is a load in between the fault and the CT. This saturation can lead to a misoperation of the differential protection. So what I need to do is I need to stop the relay to operate in case of the saturation. So I will expect the worst case scenario of a saturation of any of these CTs, and I will see the maximum slope or the maximum error can happen. Then I will plot all of them together. Then I need to sum all errors to find exactly what is the maximum error can happen in case of a normal operation. So I will draw the characteristic here, the summation, which is the summation of the error number 1, the magnetization, error number 2, tab changer and leakage, error number 3, the saturation. So at the end, I will have the summation of all of them. Then I will slightly try to change this nonlinear characteristic to a linear characteristic to have dual slope characteristic, or slope number 1, slope number 2, or we can call it differential operating characteristic. Slope number 1, mainly to cover the magnetization, to cover the tab changer, and to cover the CT ratio error. Slope number 2, mainly to cover the saturation of one of the CTs. Here, this is the philosophy of the characteristic. How can I see this? For example, I define here one of the most famous relay manufacturers. This is from Siemens. So I need to assume this case to define the characteristic. I need to assume that I have a very high large current through the protected object. Then this will cause a differential current W1 and W2. Then I correspond to the differential current IDIF. So I will calculate the minimum operating current. And this is in general what I said, that I have a relationship between the differential current function of I restraint, which is equal to I1, I2. And I restraint here, it's equal to the max of I1, I2. This is just as an example. So that's why we need to say that every time, in order to know what is the exact formula or equation for the restraint current, you need to go back to the relay manufacturer. This is Siemens relay, cyprotic 5. So it has a maximum of I1 and I2. So for example, if I have I1 here equal 1000 and this is 1500, so it will take the maximum one to have the highest security. One missing thing we didn't mention, that ID greater, which we call it the unrestrained characteristic or the unrestrained differential current. Because if you see here, if I try to go, for example, at I restrain equal number 4, so you will see that as long as the bias current increase, the differential current will increase. The value of I differential at I bias equal 4 is less than I differential equal 6 because of the slope number 2 is less than the equation of I diff at number 8. But once I reach to a certain value of I differential, the relay will trip regardless the differential current. If this not available, you will see the line will be extended, and as long as the bias current increase, the differential current as well will increase. So the I diff greater is just to cut off the line, to stop here, and whatever the value of the whatever the value of once the differential current reach to I diff greater, regardless the value of the I restraint, the relay will trip. Another thing which is important to know here, which is very important, by the way, and especially in Siemens relay, for the people who will deal with a Siemens relay, this we call it high current add-on stabilization. This is very technical thing in Siemens relay to avoid the relay to trip in case of the restraint current is increasing slowly, to avoid the CT saturation. What does it mean? It means normally, if I have a fault very close to my transformer, current transformer, and it is external fault, what will happen? The differential current will be 0, and the restraint current will start increasing faster than the differential current, and the differential current will be at the 0. But once one of the CT is saturated, then the differential current will start increase. So which current start to increase earlier than the other? The restraint current. So the relay will detect that the restraint current increasing at the beginning, and after certain number of cycles, the differential current start to increase. So it means there is an external fault plus a saturation. Because of what? Because if the fault is internal, so both of them will increase simultaneously, the differential current and the restraint current. So the relay will learn or will understand that, okay, at this case, the fault is internal because both of them start increasing together. And the other case is external fault, but one CT saturated because the restraint current start increasing at the very beginning, then later on the differential current start increasing. Then the relay will try to block the differential current, the differential protection for a certain time. And if this time elapsed, so it means no, we need to trip to avoid any failure in the protected option. This is how the idea of the current stabilization happen, and also the dual slope characteristic. Another phenomena which is very important for us, we need to understand the inrush current. What is the inrush current? The inrush current happen if I'm trying to energize a transformer today. What is the procedure? The procedure is I will keep the low voltage side open, and I'm trying to energize a transformer from the high voltage side, because it's not a common practice to energize the high voltage side on closed circuit breaker on a low voltage side, because this will lead to a huge current to flow suddenly. This can make what we call a power swing in our system. So what we are doing, we just close the high voltage circuit breaker for a certain moment. Then I'm closing the low voltage circuit breaker. This procedure will cause that the transformer maybe will be a subject for an overexcitation, because I'm energizing from one side. This will happen that, and a huge current will flow in the iron core of a transformer, so it will increase something we call it remnants or the residual flux. You can say it remnants or residual flux. and the flow and a flow current of the I magnetization current will flow in the transformer. Due to the effect of the hysteresis, you can see here, once I turn it off, the transformer, switch it off, this flux will never go back to the same residual flux because we know it's a buildup. So if after a certain number of days or a month, the transformer is energized, then I try to switch off. The flux will be reduced, but it will never go back to zero. It will go back slightly more than the remnants. Later on, I decide to energize my transformer based on when I'm going to energize my transformer, at which instant in the voltage sinusoidal wave, this remnants will increase, and sometimes it will go very high remnants or very high magnetizing current will flow inside the transformer. This is will called the inrush. The inrush is a very transient current, consists of current peaks, as you can see here, and this current peaks mainly from the second harmonic. When they analyze the current during the inrush condition, they found it's mainly of a second harmonic content because it is decaying very fast and it is like a peaks. This current, if I didn't put it into my consideration when I'm energizing the transformer, this inrush current can mislead the relay, and the relay can consider it as a differential current because it's a current flowing from one side and doesn't flow on the other side. So the relay will trip. So every time I'm going to energize the transformer, it is tripped because of the inrush current. Here you can see the magic of the numerical relay. In the old scheme, the high voltage, the high impedance, there is no way to detect the inrush. At that time, what we were doing, just we increase the setting of the relay to a very high value. Then we are energizing. Then we are reducing the setting again after energizing to avoid the trip of the inrush. But with the numerical, we can have this value. We can estimate. We can say yes, the percentage of the second harmonic content in the inrush current while I'm energizing a transformer is 20%, so I can give a tolerance 25%. So if the inrush current or the second harmonic content is less than 25%, so it means this is not an inrush, this is a clear fault, this is a differential fault, then I need to trip the circuit breaker. This is so many things I need to put it into my consideration. So I need to define so many relay manufacturers. On the left side is a GE, then Siemens is a Protec 5, then REX from ABB, then I have SCL for H7E. All of them cook with the same water, but with a different philosophy, with a different taste. So you need to go back to the manual to understand. With Omicron, we have a great solution to help you to test this current of this kind of a protection relay. With one powerful tool, we have it. It's a test universe, which our operating software and our CMC, our main horsepower, the CMC 356. It generates 3-phase voltage and 6-phase current, because in the differential you need 6-phase current to simulate the high voltage side and low voltage side. You can test all kind of these relays with the kind of automation. What does it mean, automation? That we are getting the relay settings from the relay software, importing in our test universe, then we are drawing the characteristic automatically for you, and then you can start testing very easily. So we will take a sample, which is Siemens relay. You will see what is the relay settings you need. The high voltage side, you are defining the threshold, which we said the minimum operating current, slope 1, then the intersection between slope 1 and slope 2, then slope 2, then you will define the intersection of slope 2. So you need an intersection point here, number 2, which is defined here, intersection 1, I restraint, and number 5, which is the intersection of intersection 2. Based on this, you can draw the characteristic. You can do the calculation, they can do trigonometry and find the intersection between slope 1 and slope 2, then you will draw the characteristic, and at the end, you will do some homework to understand. And as I said, in Omicron, we have something, we call it Protection Testing Library, PTL, which helps you a lot to understand the function and save your time while you're testing. At the end, you will calculate 3 points, point number 1 and point number 2 and point number 5. This is what you need to calculate if you would like to draw the characteristic of the relay manually. Point number 1, which is here, you can see if you have a direction or you have a relation between X and Y. So point number 1, what is the X coordinate for it? It's 0 because it's starting from 0, and Y is the minimum operating current, so it will be 0 and 0.25. Point number 2, it's very clear. You have the coordinate of X because it is here in the manual, X coordinate for the intersection 1, which is 0.67, and you need the Y coordinate. The Y coordinate of it, you can see the point number 2 is on the first one, the first segment, and in the second segment. So the Y coordinate of point 2 should equal to the Y coordinate of point number 1. So it will be 0.25. Number 5, point number 5, you know already the X coordinate of it, 2.5, and you need to calculate the Y coordinate. If you define the slope of point number 1, that delta Y over delta X would equal to the slope, then you can get the value of the Y coordinate of point number 5. This is very simple mathematics you can do. Then you can go to our test universe to define this characteristic. But as I said, with the PTL, you don't need to do such kind of a calculation. The parameter of the transformer, as we said, we have rated apparent power, we have the rated voltage. The rated voltage here is 231, the rated current is 400, 160, 115.5, and 800. And you can see here that I can even cover some cases which is not available in the, which is not, you can say it's a niche application. Here I have a delta winding, but it is grounded with a zigzag transformer. With a test universe, you can simulate this. It's a very niche and also very unique, and special, by the way. So you can do it even in a simple way with the test universe. What are the tests I need to do to confirm that my system is working as per the relay settings? The first one, that you need to confirm that your system is stable against the external fault. So in Omicron, we have what we call a diff configuration module. The diff configuration module, you have the characteristic of Y, you have the characteristic of your transformer. You are simulating an external fault on one side, and the fault is supplied from the other side. You need to confirm that your system is stable in this case or not. Then you can switch. You can say that, oh, hey, I don't need a fault here in the high voltage on the star side. I need it in the Z5 or in the delta side. Then you can go to the general tab, press in general, change the fault side and change the supply side. So you will see that the fault will become here and the supply will become here. It's a very, very important test to confirm that your system is stable against the external fault. This is the first requirement of any protection system, that it is secured against the external fault. What else I can do? I can test the differential configuration beside the slope. I need to confirm that if I put a slope of 0.3 and 0.7, that I need to see to understand or find that my system is really working on this slope, 0.3 and 0.7. What is the solution I have? I have advanced differential module. I'm entering the data of my transformer. I'm entering the rated power of 231, the secondary of 115, then the rated megavolt ampere. Then I'm entering the vector group. Then I'm deciding which group is the star point is grounded or not. And also I can have up to 3 winding transformer, which is a common transformer, by the way. So I can say 3 winding, which maybe YD1, D11, YY0, D5, based on your application. So you can define here any kind of the vector group, any kind of the connection diagram. Afterward, I need to define my CT, the high voltage CT, the low voltage CT, and also the most important parameter we talk about is the polarity of the CT. If my CT is toward the object, it means the P2 is to P1 is toward the object or the other side. This can happen at the star point grounding application. Then I need to define the protected object. which relay I'm testing. For example, as I said, I'm testing a Siemens relay. So in Siemens relay, you need to define here. You can see in our test universe, we didn't talk about the differential calculation because we said all of them are similar, but the bias calculation depends on the relay itself. So here I choose the maximum of I primary and I secondary because I got it from the relay manual that the bias current is the maximum of IP and IS. Then before in Siemens, you can by the way, you can go here to the bias equation in the drop down menu. You can define exactly the bias equation. We have two generations from Siemens relay. We have Cyprotic 4, Cyprotic 5. In Cyprotic 4, the equation was I primary plus I secondary over K. And here K might be 1, might be 2. It is based on the relay. But in Cyprotic 5, it is different. Maximum IP and I secondary. So you need to go to define the K factor from the relay manual. No combined characteristic. This is a special application for ABB relays, RET 670. You will see in the next slide how it looks like. Then you need to define the maximum operating time, the maximum differential current, the IDIF greater, IDIF greater, and you can define also what is the reference winding. Is it the star or it is the high voltage? Because some of the relay, they are looking for the star side, some of them looking for the high voltage regardless, it is delta or star. Afterward, you will go to the characteristic and you need to calculate the 3 points as we said, 0.1, 0.2, and 0.5. And then you will draw the characteristic and you will see the characteristic looks like that. And at the end, you test the characteristic and you see now the differential characteristic for single phase fault and the differential characteristic for phase to phase and 3-phase fault. You can see here, the color is pink. This is due to the non-combined characteristic of ABB relay. For more details, you can feel free to contact me. I will explain it. We have application note about the non-combined characteristic, but here briefly, it will have some effect. It will have some effect. It will have some effect on the in the slope or on the color. You will see here two slopes, two different slopes, even it is in the same characteristic. This is what we call it the parameter testing. I'm testing now the parameter I have entered to the relay: slope, CT ratio, polarity, the harmonics content, the CT ratio, the rated power, the rated appearance, the rated volt. This parameter I entered. But am I sure if I install this relay in this system, the relay will trip correctly or not? Here, I need to think beyond this, beyond the parameter, the performance test. Now I have ABB relay as a main one, because in substation, usually we have a main one and main two. So I have ABB relay and I have a Siemens relay. If I put all of these two relays together to protect the same transformer, am I sure this will work together or not? Here, we need to think about something different or something we can say more reliable. We call it system-based testing. In Omicron, we introduce a solution, we call it relay sim test, which you can draw the relay characteristic. You can draw your power system. You can think about any scenario can happen while this transformer running, and you can see, yes, this protection relay with this setting can protect my system or not. And right now we are working with SAC, Saudi Electricity Company, to have the relay sim test as a testing solution at the end to check the performance of your network and also the system stability. I need to draw the in-feed. As you can see, I need to draw the in-feed. I need to draw the transformer. I need to draw the current transformer, CTA, CTB, and also I need to draw the load. This is very, very nice, very, very easy. I will define the in-feed based on my system. I'm pretty sure that every protection engineering department, they have the short circuit, they have the nominal, they have the short circuit impedance, they have the nominal voltage, they have the propagation, they have everything about the in-feed. The transformer, you can get it from the nameplate of the transformer. The CT, because you tested the CT on site with our product, for example, you have a CT analyzer, then you can get the CT a characteristic and CT result from the CT analyzer, edit CT data, then import to the relay sim test, and you will have the real value from the CT, which is available on your transformer, not from the data sheet, not from the factory acceptance test written. No, you can get it as an XML file from the testing equipment where you test the CT. Then you can define the transformer, the number of windings, the short circuit voltage, the percentage impedance, the core type, the no load is how much the no load current, the grounding of a transformer, if it is grounded or not, the full detail of a transformer. To have what? To have the next slide, you are simulating a very close fault to one CT at the high voltage side, and at the end you can simulate a current transformer saturation and see if your system really respond correctly or not. Because the case which I faced a lot and confront a lot, that I am going on site and I found that I have a transformer, for example, was protected with two different relay manufacturers, and finally I go there, I found that main one operate, main two operate. This is the confusion moment for any protection engineer. Which one operates correctly? The one which tripped or the one which didn't trip? Then you need to calculate everything and to ensure that maybe this has a sensitivity issue, it doesn't trip, or maybe this is oversensitive, so it's a trip. So you can avoid this moment, confusion moment, with a pre-testing. Draw your system, simulate the same fault to both relay simultaneously and see, and expect the worst case scenario in your system. And finally, you can see and decide, yes, my system works fine. So I tested now the parameter which I enter, and I tested the performance. And at the end, this is to improve the network reliability and also the key performance index for the substation and the equipment. At the end, thanks for your interest. I'm just sharp at 1 hour, and I'm very open to answer all your questions.
Thank you, Engineer Ahmed, for a valuable presentation. And we will go ahead and take 10 or 15 minutes for questions. Now, just remember, please be sure to type your questions into the question box in your control panel in Zoom, or raise hand button to ask directly to speaker. Here in Engineer Ahmed, some ask about explain stability test by Omicron.
Yeah, I will go back. So stability test, it's a basic test and a very important test. Why? Because, for example, I can't go to test the characteristic and I'm not sure that my transformer is stable or not in case of an external fault, because we have two main requirements for any protection system. The first one, that my system is stable and secure against external fault. So what I'm going to do is, I'm very clear, just entering the data of a transformer, and I will simulate a fault with any value. Here I simulate a fault with 1 I nominal, that the transformer will carry the full load current, then 2 full load, 3 full load, and I can go for 100 full load if my relay can withstand, and also my CMC can inject. Then what I'm doing, I'm just injecting and see. The expectation is that in case of my system is stable, so I shouldn't have any differential current. So we will say it's 0, and the bias current should equal to the value here. And you can see here, the I test is not the differential current. I test here, it is the bias current, because I'm simulating a current. I'm simulating a stable condition, and the stable condition that there is no current should flow, no differential current should flow, because that my system should remain stable. So for example, here, if I inject 1 per unit as a bias current, the second will be 2 per unit, 3 per unit, and the differential current will be 0. Afterward, then I will say that my system is completely stable. There is nothing, because maybe you will have a wiring issue. Maybe your protection relay is fine, but wiring, while the commissioning engineer is doing some kind of a modification, he just swapped two phases, red instead of yellow, yellow instead of blue. So if you start doing the trip test and you define that your system is tripping all the time, you don't know what exactly the problem. The problem is in your calculation, in your CMC, or in your injection, or in your relay, or maybe it is a wiring. So to minimize the number of reasons of the mistake, so what we are going first, stability against external fault at both sides, side 1 and side 2. If you would like to if you are interested more about the way what we are testing, feel free, please. You can drop me an email. I will send you a video in Arabic and in English for testing a complete transformer differential protection relay with more details. Thanks, Engineer Ibrahim, for any question.
Yes. Here in Abdul Sattar ask if the transformer connected directly to generator, the differential curve, how will be?
Again.
If the transformer connected directly to generator,
yes,
the differential curve, how will be?
It will be, yeah, it's a very good point. If you remember what we said the generator itself doesn't have any, influence about the differential protection, because the current in equal to the current out. So we will consider it as a bar, as a conductor, nothing at all. I will take the CT before the generator at the neutral side, not on the term and not on the line side, and I will take the current of the CT for the transformer. I can draw it for you here. Just a minute. Okay. So it is very easy. I will just here. I will have, for example, this is the conductor. I will have here a CT. This is CT from the neutral side of the CT of the generator, and the other CT will be here at the high voltage side. And in between here, you will take the CT. They will take the generator and the transformer, nothing else. Then this CT from the neutral side of the generator will be the low voltage side of the transformer, and this will be the high voltage side of the transformer. And the generator doesn't have any effect on the characteristic itself. It might take more errors, but in the slope, no. Okay, Engineer Ibrahim?
Okay. Maybe it's look like we have covered all of our questions. Engineer Ahmed, is there anything else you wanted to cover before Arabab?
Thanks a lot. Just I would like to show you something before we leave. To take the opportunity, I will just open an OCC file. This is an OCC file from Omicron Control Center, where you can do everything related to the protection. Here you can see it looks like that. Here we have the OCC file, and in the OCC file, it's very easy way. It's like a container, and in the container we have everything. We have everything available there. So what you need to do is just to go to the relay software, export the setting from the relay software, import here in our test universe, and the test universe and the OCC file will calculate the complete characteristic of everything. And finally, you will go here, for example, for the diff configuration. And you will see here that I was testing a transformer of YY0D5. So I have a transformer, 3 windings, star 0 D5. And I want, for example, now to change the location of the fault. Because it's already tested, I need to go here, clear. You can see here, the fault is in the left side. I need to have the fault here in the right side. I will go to the general, then fault primary, supply secondary. I will say fault secondary, supply primary. You will see that the voltage, the fault change to the other side. The supply will be from the primary side, and it will flow inside the relay. If my system is stable in this case, so it means it is stable in case if I have external fault in this side and in this side. What else I can do? I will go to test data, change at any value here. For example, 10. And I have three faults with a different bias value, and I expect that the differential current will be 0. This is related to the stability. And I can go here, for example, for the operating characteristic. You will see here that I have a different bias equation, different bias value. And my CMC, what is going to do is, let me clear it. Afterward, you will see that I can have a different bias values, and the CMC will inject this, and it will go here in this area, simulate a fault, the trip, and it will go to this area and simulate a fault that it doesn't trip. So it will detect there is a line here. Then it will minimize the step of the movement till it finds the intersection between the search line and the characteristic. From here, you can see the lowest dotted line, it's IDIF greater, which is the minimum operating current. And here I have IDIF greater, which is the unrestrained, and the relay characteristic. What is the last line, which is this line? It's a line of a 45 degree, because electrically, we don't have any possible way to have a fault in this region. Why? Because if you have a fault in this region, so it means there is a third current source which you didn't put into your system. What does it mean? Do you remember that when we say that I have a fault, I have a node here, and this current is going to each other, and ideally we said this current equal to this current. So if this and this going to the same point, so it means both of them are equal. So if you submit both of them vectorially and scalar, so you will see that it is I plus I. This is I differential, so it will be 2I. And the other one, which is scalar, to represent the bias current, this will be I plus I, so it will be 2I. So the differential current will be 2I, the bias current will be 2I. And if you draw a characteristic, it will be a line passing through the origin with a slope number 1, which is a tan delta of a 45 degree. This is from my side, Engineer Ibrahim. I hope we can meet soon, and please feel free to contact me at any time for a practical session or even for any question.
Thanks,
Dr. Ibrahim.
Thank you, Engineer Ahmed. And one questions I will take Engineer Muhammad Saad to contact you by emails to any question, and Abdul Sattar also. Great. Thank you, everyone. Thank you, Engineer Ahmed. We appreciate your being here. Thanks again for joining us today, and we will see you next time. Good night, everyone.
Thank you, and nice to meet you.
Thank you.
Assalamu alaikum.